All right, ladies and gentlemen, as we close up chapter 3, we are going to start looking into some real life application of our exponential and logarithmic models. So, the goals of this video are to recognize what the 5 major exponential and logarithmic models are and to implement these models in real life application. Now, we are not going to go over an example of every single one of them, but we are at least going to identify them and be able to see how to recognize them in a problem specifically. So, let's first and foremost talk about one that I think most of us are well aware of, and that is the exponential growth model. All right, in which the key thing about the exponential growth is the restriction for the exponent, and that is because it keeps it positive. When e to the x is remaining positive, that means we are constantly seeing growth. Think about what it meant to compound continuously when we started talking about our investments, right? In our investments, it should be constantly growing if time is staying positive, which obviously it has to, and our interest rate is staying positive. If your interest rate gets negative, that's when you have a little bit of a problem there. So we don't want that to happen. All right, so let's take a look at an example of how can we utilize the exponential growth model here. All right, so it does say in the table, and if you want to take a look in your books, it's on page 237 of the table that we are given here. But basically it says an exponential growth model that approximates the data, all right, of the world population can be written from P equals 5,340 times e to the 1.2922% times t. As long as t is between 5 and 13, because we are dealing with years 5 and years 13 in this particular example that we have. All right, so let's think here for a sec. All right, t itself represents the initial, t equals 5, excuse me, represents the initial year. And that initial year on that table is 1995. So that represents the initial starting point for it all, okay? And it says, when specifically will the world population be 6.8 billion? All right, 6.8 billion. Now, on the table specifically, everything is not in billions per se. All right, we've condensed it on down to what we are looking at. Okay, so 6.8 billion is going to be represented as 6,800. Okay, 6,800 as that is what the model shows us, because 6,800 millions, right? So 6,800 millions is 6.8 billion, okay? So that's when you're going to see the 6,800 here in a sec. That's because 6,800 millions is 6.8 billions, because the population on the chart is in millions specifically. All right. So we're asking ourselves is, when does the population become 6.8 billion? So we're asking ourselves is, when does P equal 6,800? That is what we want to take away from this scenario. Okay, so we're saying, hey, when do we see 6.8 billion happening, or 6,800 millions in this case? Well, this is just a basic exponential function or exponential equation that we're going to be solving for. I'm going to go ahead and first and foremost divide by 5,340. And I roughly get about 1.27341 equals e to the 0.012922 times t. Well, now, how would I get t by itself or out of the exponent? Just like it was before, you would natural log both sides. And that cancels the natural log, cancels the e, so natural log of 1.27341 equals 0.012922t. And then we solve by dividing by the 0.0129. And then in the end, we end up getting t roughly being about 18.7. All right. So this is when in the 18th, between the 18th and the 19th year is when you are going to see this in fact. All right. So somewhere in between 2008 and 2009 is when we're going to be, seeing these particular things come on into play. Okay. All right, guys. Let's continue to push forward a little bit and take a look. Well, I want you to go ahead and give this one a shot on your own. And the concept that we're looking at here is what if the model is not given to us, right? What if they don't give us a model to use? So I challenge you, pause the video, give this one a shot on your own, and see what happens when you're given an example in which a model is not given to you. It's your job to find out what the model is. Pause the video now. Give it a shot. All right, so example 2. In a research experiment, a population of fruit flies is increasing according to the law of exponential growth. So we know what to expect. We know what to expect from the model. After 2 days, there are 100 flies. After 4 days, there are 300 flies. How many flies will be there after 5 days? Well, in situations like this gives us information about a scenario specifically. We know the exponential growth model gives us y equals a times e to the bt. And in 2 different scenarios, 100 flies were produced when specifically there was 2 days involved. And on the other side of things, 300 flies were produced when there was 3 days being involved. Okay? And so now we utilize this information to go ahead and to specifically solve for our missing variables. But the problem is we have both A and B that we need to solve. So I'm going to actually utilize one of my equations to put one in terms of the other. I'm going to go ahead and solve for A by saying A is equal to 100 over e to the 2b. Do we all see that? All I did was just get A by itself. That's all I did. Now I can use this information to substitute it into my other problem. So 300, we just said A was 100 over e to the 2b times e to the 3b. Now everything is at least in order here. Well, take a look at what happens here, folks. We all agree this is 300 times 100 times, or equals 100 times 3b, right? Over, oh, I'm sorry, this is 4b. Did I put 3 here? I'm sorry, guys. Let me backtrack a little bit. I don't know where I was getting 3 from. This is 4. It was 4 days, not 3 days. Let me backtrack this just a little bit. Hopefully you caught on to that, okay? So this is actually 4. I knew this wasn't looking right. All right, and do we agree that when we divide, this is the same thing that we're happening on over here, right? Why is this beneficial? Because when I divide 100 on both sides, I get 3. And then this is the law of subtraction of our exponents. E to the 4b over e to the 2b is e to the 2b. Now we're getting somewhere. This is pretty simple stuff for us. So now we can natural log both sides, and we get that 2b equals the natural log of 3. We can divide by 2 to finish it on up to say that b equals the natural log of 3 over 2. All right. So now we've gone ahead and found out what b actually equals. So now we can go back into our original equation for a and say a is equal to 100 over e to the 2 times the natural log of 3 over 2. And this will allow us to solve for A specifically, or in a sense, we end up getting roughly around 33.3, give or take a few. All right, so now we have A, and now we have B, and now we have our actual model that we can use. So I'm going to throw my model up in here. Y is equal to roughly 33.3 times E. B, I'm going to simplify this on out, guys. B, the natural log of 3 over 2, roughly comes out to be 0.5493 to the t. Now I can use this model for any of our situations. And what it wants in the end is a situation of 5 days. So now substituting in for 5 days, let me just change some colors so we don't get too confused. Y is equal to 33.3 e to the 0.5493 times 5. Roughly, guys, this came out to be about 514 flies in the end. A lot of work, I know, but a lot of good stuff as well, too. All right, guys, that's going to close up shop for this video specifically. And the next video, we're going to dive on into exponential decay, a little bit of the Gaussian model, and some others as well, too. On to the next one.